Functional groups and experimental skills. In this particular video, we are going to talk about the functional groups, what they are, how to recognize them, and how to identify them in a complex organic molecule. So let's start by defining the key players of organic chemistry. The first one is known as the alkane group. And alkanes characterize themselves by having only carbon-hydrogen bonds and carbon-carbon single bonds. If that's all your organic molecule contains, you got yourself an alkane. And in terms of the number of hydrogens, from the point of view of the number of carbons that your alkane has, there is a simple equation that tells you that information, and it's simply Cn, where n represents a number greater than 1, equal or greater than 1, and H2n plus 2. So if you have 2 carbons, 2 times 2 will be 4, plus 2 will be 6. So 2 carbons can take up a maximum number of 6 hydrogens. If you only have 1 carbon, 2 times 1 will be 2, plus 2 will be 4. So 1 carbon can only take up maximum of 4 hydrogens, and so on and so forth. This is actually a formula that we use a lot in the determination of unknown compounds, and we'll talk about that later in the class. But it'll be useful for you to kind of get used to remembering this formula, CnH2n plus 2. That's the maximum amount of hydrogens any organic compound could have. Then there is the alkene family, okay? And don't confuse, I know the names are very similar. This is alkane, and this one is alkene. And the alkenes are different from the alkanes in the sense that they have carbon-carbon double bonds, and they only need to have at least one of them, and you already have an alkene. This is no longer referred to as an alkane, but rather an alkene. And if you have more than 2 alkenes, it will still be referred to an alkene, right? That doesn't really change. The interesting thing about it, though, is that for every one double bond that you introduce in your organic molecule, you end up needing less hydrogens. In particular, you need 2 less hydrogens for every double bond that you have present. All right, then there's the alkynes, and the alkynes are simply molecules that contain carbon-carbon triple bonds within it. You could have at least one of them, you could have 5, 10 of them, probably it'll be very unlikely you have that many triple bonds, but at least if you have one triple bond present, you got yourself an alkyne. And the presence of an alkyne decreases the number of hydrogens by another 2. So in the case of the alkane, this was 2n plus 2. In the case of the alkyne, if you only have one triple bond, this decreases the number of hydrogens by 4. Something that we make use of in the future for identifying unknowns. All right, now what I do like to do with this type of table is kind of arrange carbonyl compounds, and by that I mean compounds that have carbon-oxygen double bond functionalities in relation to the groups that I'm presenting here. So if you look at the alkane and you simply put that CO group on this middle carbon, this will create a new functional group. One thing to notice is that the carbon of this carbonyl functionality is bound to 2 other carbons. So the R here represents carbon in all of the structures. So we have carbonyl carbon bound to 2 other carbons, whereas right here carbonyl carbon is bound to at least 1 hydrogen. And this presents you with 2 different functional groups, the ketones and the aldehydes. Ketones are the molecules where the carbonyl is bound to 2 carbons, 2 other carbons, and the aldehyde has the carbonyl carbon bound to at least 1 hydrogen. And the hydrogen has to be directly bound to that carbonyl, or else you don't have an aldehyde. Okay, so that CO double bond is definitely a prerequisite, but also what's bound to the carbonyl carbon dictates what functional group you have. Ketones and aldehydes, and their chemistry is actually not super different from each other, but having an aldehyde versus a ketone means that your reactions tend to be faster, just because you have more room available at the carbonyl where most of the chemistry happens. All right, now let's move on to another set of functional groups. These are the ones that contain carbon-oxygen single bonds, but in addition to that, the oxygen atom has a hydrogen bound to it. Collectively, this is known as the alcohol family. And you do need to have the hydroxyl fragment bound to carbon for this to be an alcohol. If you take that same alcohol functionality and simply change this carbon to a carbonyl, such that now the carbonyl carbon is bound to an OH, this becomes a carboxylic acid, and it is a different functional group than the alcohols, much like the ketones are a different functional group than the alkanes. Ultimately, what this means is that the chemistry and the reactivity of a carboxylic acid will be different than that of an alcohol, the same way that the chemistry of a ketone will be different than that of an alkane. In particular, something we'll observe later on in future lectures is that, yeah, carboxylic acids do have more acidity. They're more acidic substances than alcohols, and we'll investigate and talk about the reasons why in future lectures. All right, so we have that CO double bond in carboxylic acids that allow you to have your carboxylic acid so long as you have that OH bound directly to the carbonyl. The other option would be to have a carbon-oxygen single bond, but then that oxygen is bound to some other carbon. So you end up making these COC molecules, your ethers, right? So C, O, and then C, whatever this R group, alkyl group ends up being. But you get yourself an ether. And if you take that CH2 that we have here in the middle and you replace it with a carbonyl group, so that in this case you have the oxygen, the COC fragment now directly bound to the carbonyl, you got yourself a different functional group known as the ester. And it is important to point out that for the carboxylic acid, the ester, and the amide that I'm about to present, the carbonyl has to be directly bound to the OH or directly bound to the OR or directly bound to the nitrogen as it's shown here. If that's not the case, then you do not have a carboxylic acid or an ester or an amide. Okay, now since we've introduced this functional group, we talk about the carbon-nitrogen bonds. This is a new family. This is known as the amine family, and these tend to be the stinky compounds. They're not the worst compounds in terms of smells that I've ever encountered in organic chemistry, but they tend to be a little bit foul. Now, amines characterize themselves by having at least one carbon-nitrogen single bond linkage somewhere within the molecule. And if in addition to that you have a carbonyl to which the nitrogen is bound to, you got yourself an amide. All right, so same idea. Nitrogen has to be directly bound to the CO fragment for this to be an amide. Here you have a little bit more variety though, because you could also have molecules that have a carbon-nitrogen double bond, and they bear a name very similar to amines. These particular fragments are known as the amines, and they represent a functional group of their own. They have that carbon-nitrogen double bond, and you could even have carbon-nitrogen triple bonds, which are known as nitriles. Right? And these ones, they have a very different name than the rest of the family. However, the N is basically kind of emphasizing the fact that this is a triple bond to a nitrogen, right? But slightly different name. And nitriles tend to be actually really good solvents in general in organic chemistry. A lot of people use acetonitrile. That's a common solvent, so it's very common. The last functional group that I should mention to you is the aromatic functional group, which is best represented by the hexagonal structure here with three alternating triple bonds known as benzene. And you'll do well to remember the benzene ring because we're going to use it, in many different examples in the future. So this is an important group. And in the class, we're going to be focusing a lot on the alcohols, the alkanes, the alkenes, the alkynes, the ketones, and the aldehydes. In the second semester organic chemistry course, that's when you get to really emphasize the chemistry of carboxylic acids, the esters, the amides, and the amines, and also the aromatics. But we will talk a little bit about aromatics in this class, and to some extent, some of the carbonyl compounds will also be integrated in here. Okay, so now let's take a look at some of these big molecules and see, if we can identify different functional groups. It is not necessary to have just one functional group in a molecule. You could easily have a wide variety of functional groups in the same molecule, and you just kind of have to identify them. For instance, look at this molecule. If you look at the segment highlighted here, well, that's a carbonyl compound, but the carbonyl carbon is bound to a carbon and another carbon. Therefore, this is a ketone. Then, right above it, you see this triple bond. Okay, and this triple bond is just one between carbon and carbon. So those two carbon atoms are forming a triple bond. That's nothing more than an alkyne. Okay, moving further to the right, we'll look at this particular group. This is an OH functionality bound to a carbon. So technically, this is an alcohol. But it happens to be an alcohol bound to a benzene ring. So this is an aromatic alcohol, and it has a very common name that we use often in chemistry. It's known as a phenol, and the phenol functionality has it's very similar to alcohols, but it has other aspects of it that kind of distinguish it a little bit. But it is still an alcohol. So if you tell me that this is an alcohol, that's correct. If you say that it's an aromatic alcohol, that's correct as well. I would definitely, look fondly at that, because be like, okay, you are really seeing the contrast of these things, but they are alcohols nonetheless. And speaking of which, we look at this regular OH bound to a carbon. Okay, this is not aromatic, but it is your alcohol, right? This is not next to a carbonyl, right? So that not CO double bonds. And notice here that this carbon is bound to another aromatic, but the O is not directly bound to the aromatic. So this is not an aromatic alcohol. This is just a regular alcohol. All right, now looking at the fragment right here, we have a nitrogen bound to carbon, and bound to another carbon. Now, the fact that the nitrogen is bound to directly to an aromatic carbon means that this is an aromatic amine. And it has a very unique name as well. So, whereas the aromatic alcohol is known as phenol, the aromatic amine is known as aniline. And those are names that you probably come to use a lot in the second semester organic chemistry class, but I'm just trying to make you aware of them right now, as you may encounter them in labs. Okay, now down here we have another fragment. This is a carbon-carbon double bond. This is your alkene. And over here we have just another benzene ring. Notice here that in all of the structures, in fact, the benzene ring, instead of having the three triple bonds, I've just drawn a circle. And the reason why is because via resonance you can alternate the positions of those double bonds. And so this is a much more accurate representation of what's going on inside the hexagonal planar structure right here. And that's your typical benzene ring. So this is your aromatic group. But if the aromatic group is bound to a CH2, we call this the benzol functionality, but it is aromatic nonetheless. Okay, let's do one more. Here's another funky structure. Let's look at this fragment right here. Now this is technically a nitrogen bound to just regular carbon, so this is your amine. But one of the carbons that is bound to is a double bond or an alkene fragment. So this, I didn't mention to you in the previous slides, but I just kind of want you to be aware of. This is kind of its own subset of functionality. This is an alkene plus an amine is known as an enamine. And you will encounter reactions like this a lot in the second part of organic chemistry. They actually play a big role in the chemistry of carbonyl compounds. Okay, now then this one right here, you have a carbonyl group. Now that carbonyl is bound to a carbon, so you might be tempted to say that this is a ketone. However, the other end where there is nothing bound to it, well, this is only 3 bonds, so you have to have a 4th bond to a hydrogen to complete the octet of this carbon. So this is actually, in fact, an aldehyde. Okay, moving on. Down here we have this CN fragment, which I mentioned to you earlier. Whenever you see CN like this and nothing more beyond the nitrogen, this is your nitrile group. This is a carbon-nitrogen triple bond. And speaking of triple bonds, we have this other fragment right here, which is only made up of carbon and carbon in between. So this is your alkyne. Over here, you have an oxygen bound to carbon and bound to another carbon. This is your COC fragment. And the oxygen itself is not bound directly to a carbonyl. So this is an ether. On the other hand, over here we have a carbon with 2 oxygens and an H. If you spell this out in terms of Lewis structure, you'll find out that this is nothing more than your carboxylic acid. So it's a good idea to get used to looking at the carboxylic acids written in this manner, as well as drawn out with a carbonyl with an OH bound to them. And the same thing goes with the group up here, which is an amide. This O, which is next to the carbon, is your carbonyl, CO double bond, and the nitrogen is bound to that same carbon, which is the carbonyl carbon. Therefore, this is your amide. So these are the things you have to kind of be aware of when trying to determine, what you have present in your molecule. And same thing here. You have an ester. Now the Me, I haven't introduced this abbreviation just yet, but this is a CH3 group. And so what you have here is a C with an O forming the carbonyl, and then an OC bound to that carbonyl. So you have your COC fragment, and it happens to be a carbonyl fragment as well. So this is your ester molecule. Okay, so in the next video, we'll talk a little bit about intermolecular forces, and we'll kind of proceed from there. So see you in the next video.